periodic table. So in this video, we have lots of memorizing, so we're just going to go over it. And you have to take the time to memorize stuff. You can also use the book to go over it and read more. So periodic table founded by Mendeleev, as you've heard about it. So he started to put elements by the atomic mass and figured out the repeating properties. But he still had some question or problems that some of the elements were not fit into the right position. So let's go to the next slide. So as I said, he ordered the elements by atomic mass and saw the repeating pattern of properties. So he came up with a periodic law that elements are arranged in order of increasing of atomic mass, which we later understand that it was not right. It should be in atomic numbers. Have certain sets of properties that recurring periodically. So what he did, he put the elements with the similar properties in the same column and come with a table. So we use the pattern to predict the properties of some undiscovered elements at that time. And in places where the atomic mass order did not fit, he reordered them by other properties. Example with tellurium and iodine. So as we said, since he was ordering it with atomic mass, some of the elements didn't match to their column, so he replaced them. But later on in the periodic table that we have right now, they figured out that they have to order with the atomic number, not with the atomic mass. So this is the periodic table. Well, it's a simple small size periodic table. So when we order the elements with the atomic number, you see that the color with the elements with the same color have the same properties. And this thing happens. I mean, it's just regular pattern. It has a regular pattern that these elements just repeat. So if we put these same colors in the same color, we come up with this simple periodic table. As you can see, you have the first column. So in the periodic table, the horizontal row, like this, the horizontal row are called periods. We have period 1, period 2, and the vertical columns are called groups, and that's where the element have the similar properties. Okay. So this is the periodic table that we have now, and we are going to classify elements in the periodic table with different means. So the first one that we have in this slide is classifying them into metals, nonmetals, and metalloids or semimetals. So it's easier to memorize the metalloids with this color, and so we know you can memorize this pattern. Well, you always have access to periodic table, so if you memorize the pattern, you know which of the elements are metalloids. So you remember these, then the elements on the left side of the metalloids are metals, and the ones on the right are nonmetals. So everything to the right of the metalloids are nonmetals, and everything to the left side of the metalloids are metals. So the other classification of the periodic table elements are they divided into the main groups in green and the center groups in the center of the periodic table. They are called transition metals, and they are all metals. In the main group, as you see in the previous slides, we have metals, we have nonmetals, and we have metalloids. in the elements in the middle are called transition metals, and we also have these groups here. They are called inner transition metals. So inner transition metals. Okay. So in the main group, some of the groups are more important and they have a name. Okay. So the first group from on the left are called alkali metals. The second group are called alkaline earth metals. So you can refer to your textbook and read some of the properties of these groups. And we have the group on the left side as noble gases. They used to be called as inert gases because they thought they're not going to react with anything, and they call it inert, which was true to some point. And then they find some compounds that has the quote-unquote inert gases reacted with something, so they changed the name to noble gases. But in general, the noble gases are pretty much happy with what they are, so they don't want to react with anything else. And you can find the elemental atomic atoms as the gas, like helium, neons. So they are just as an atom, and they do not react with anything. Well, in most cases. And the second group from the right are halogens. So we have halogens as fluorine, chlorine, bromine, iodine, and as I said, you can read more about these groups on the textbook. So metals, in general, they have some properties, and it helps when you classify them, the elements in metals and non-metals. So if it's a metal, it has these properties. Like metals, most of them, or let's say almost all of them, are solid in the room temperature except mercury. So that's the only one which is liquid in the room temperature. They have reflective surface, they're shiny, they conduct heat and electricity, they can be shade to anything, they can be used as wires. This one is important, and we're going to use this in the next video. So they lose electron. So all metals, they lose electron and make cation. Okay, so all the metals lose electron to reach and you will learn more about this in the future, about the electron configuration and the noble gas electron configuration. So most of the elements wants to reach the electron configuration of the noble gas. So that's why in metals they lose electron to become a cation in the reaction, where we see in non-metals they gain electron to reach the next noble gas in their period. So that's the important one. So metals lose electron to form cation. Okay. And as we saw in the periodic table, 75% of the elements are metals. Non-metals are exactly opposite. So first of all, you can find non-metals in solid, liquid, and gases. You can see in the example here, we have chlorine as gas, bromine as liquid, and sulfur is solid. Then that's the standard state. So unlike the metals, they are poor conductor of heat and electricity. The solid ones are brittle, you cannot shape them. And this one again, they gain electron and form anions. Okay, so non-metals gain electron to form anions. Metals lose electron to form cation. For the metalloid, on the other hand, we have the properties of both metals and non-metals. Silicon, for example, is shiny like metals. It conducts electricity like metals, but it does not conduct heat very well like non-metals. And it's also brittle like non-metals. So as I said, nonmetals have, metalloids have properties of both metals and nonmetals. They're also known as semiconductor, and there is a huge area of research on the semiconductors. Silicon, for example, you hear the name Silicon Valley, that's coming from the same concept. So ions and the periodic table. So we talked about the concept of how metals and nonmetals prefer to lose or gain electrons. So metals tends to lose electron and forming cation, and nonmetals prefer to gain electron and form anion, and they reach the same number of electrons as the nearest noble gas. The same thing with the cation. So they want to get the number of electrons of the noble gas, or electron configuration of the noble gas. And that's the basis of forming the bond. So we will talk about this more, of course, but we're just going to mention a little bit. So in a chemical bond, it could be an ionic or covalent bond. So the compound that is formed with an ionic bond is ionic compound, and when we have a covalent bond is molecular compound, and we're going to talk about more in the next videos. When there is an electron transfer, so that basically needs to be a metal with a non-metal, right? Because metal wants to lose the electron, so there should be something to gain the electron, so there should be a non-metal. So if it's between metal and non-metal, it's going to be an ionic electrons transfer, ionic bond. And if it's between two non-metals, it's usually what happens is just sharing the electrons. So both non-metals have some electrons, they share and they make bonds. So that's become the topic of ionic and molecular compound, that we are going to talk about these in the next videos. You don't need to memorize this stuff for now. Okay, so as we said, metals form cation and nonmetals form anions. So these are the common charges for the element in the periodic table. So something that makes it easier to memorize, you see that all first group metals, they have +1 charge. Okay, they all have +1 charge. It's common that they write it lithium plus, well, for one it doesn't matter, so never mind. Yes, they have +1 charge because they want to lose one electron, and when they lose the electron, they get the number of electrons as the previous noble gas, which is helium. For lithium, it's helium. Like in sodium, it loses one electron, so it has the same number of electrons of the previous noble gas, which is neon. Okay, so you see all of them just happens the same thing. Okay, so they just lose one electron, and when they get the electron configuration of the noble gas, they are happy and it just stays there. Okay, so all of them have +1. On the other hand, on halogens, here you see that all of them have -1. Okay, the same reason, they just get one electron and have the same number of electron as the next noble gas, and they are happy with that, so it just stays like that. Okay, so all the elements in group 7 or 17 have -1 charge, and all the ions in the group 1 has +1. The same on group 16, you see they gain 2 electrons. Okay, the same thing, they reach the electron configuration of the noble gas, so all of them are 2, and 15, all of them are -3. And the same thing on group 2, it has 2 +2 charge on all of them. On elements in the transition metals, you see some of the elements have 2 common charges. For example, iron, you will see iron 2 and iron 3. Okay, you need to memorize these ions that has 2 charges, and we are going to use them in the next videos when we are going to naming the ionic compounds. Okay, so chemical formula representation. So when we see a molecule, chemical formula representation, there are different ways of showing a chemical formula. Okay, the first one is the molecular formula. The information you get from the molecular formula is the type of elements, type of atoms, and the number of atoms. So for example, in CH4, we know that it has 1 carbon and 4 hydrogen. Okay. The next is the structural formula, and any of these that we are going down, it has all the information that we have from the previous one plus something else. So in the structural formula, again, we know that we have 1 carbon and 4 hydrogen. We also know that how these atoms are connected together. We know that all of them are connected to the carbon. It's not like, for example, that's not possible, but if we do not see the structural formula, maybe it's like this. Well, it's not possible, but just in case, I mean, just want to come up with an example. So the structural formula shows that how these atoms are connected together, and it should be like that. Let me erase this. Okay. Okay, so the next one is ball and stick model. In the ball and stick model, we know the type and number, we know how they are connected. We also know that the geometry of the arrangement of the hydrogen. We know it's later you will learn about tetrahedron, that's the geometry of the molecule, but that's how the atoms are connected together in 3D structure. And the last one is a space field model. In the last one, we know all of the previous information. Also, we know the relative size of each atom. You see that the hydrogen is this big and the carbon is this big. So it shows the relative size of each element. Okay, we talked about ions. That we have cations and anions from metals and nonmetals. So these ions have charge, and you know opposite attracts, right? So anions attract cations. They have negative charge, they attract positive charge. So if you have lots of these ions next to each other, think about I think all of you have seen the magnetic balls, small balls. It's not like it's each atom. If you think about each atom as a ball, it's not a great example because the magnet has 2 sides, but if you think about all of them have just 1 pole, and then we have another bunch that has the other pole. So if you mix them together, you're going to have a big cluster. Okay, so big cluster of magnets. So that's what happens when we have cations and anions mixed together. So we make a big cluster of the compound. Okay. So for titanium dioxide, when we have titanium 2 plus, and well actually it's 4 plus, and oxygen 2 minus. So when they mix together, they attract together and they form something like this. Okay, so it's hard to say what is the molecular formula. Okay, because you don't know, you're looking at this part, or let's say this part, or the whole thing, and actually this thing grow and until it makes a big chunk. Okay, so there is no clear molecular formula. So what they do, they just see how many of the total titanium and oxygen it has, and then they divide it by a common factor until they come up with the simplest whole number ratio. Okay, and that's what is called empirical formula. Okay, so if you divide the total number of titanium with oxygen but with the same number, you will get TiO2. Okay, and that's the empirical formula. For the molecular formula, we don't know because we don't know what scale we're going to look at. Okay, it's just forming a big cluster. Okay, and that's happened when we have ionic compound. But it happens that sometimes when you have a molecular compound, something like benzene, for example, it can be found as a single molecule, and you see the model how they are connected together. So you have 6 carbons bonded together, and each of these 6 are connected to 1 hydrogen. Okay, so the molecular formula tells us how many atoms are there, and that's C6H6, because in each molecule we have 6 carbon and 6 hydrogen. The empirical formula on the other hand is the simplest whole number ratio. Okay, so if you have 6 carbon and 6 hydrogen, what is the simplest whole number ratio of the atoms? You can divide both of them by 6, right? So if you divide it by 6, you will get CH. Okay, so we have molecular formula that shows all the actual elements contained in the molecule. The empirical formula is the simplest whole number ratio of the atoms. So based on what I said, which of these two best describing the empirical formula? So you probably chose number 2, which is right, because the first one, the actual number of each atom in a compound, is called molecular formula. And lowest whole number ratio of atoms is called empirical formula. So now that we learn about empirical formula, what is the empirical formula for C4H8? Well, so as we said, we have to divide them by the same number. Okay, so if we divide both of them by 4, we will have C, and we don't write 1, and H is 8 divided by 4 is 2. So therefore, number 4 is the empirical formula, CH2. Okay, so this is the end of this video, and we've learned about periodic table. You can, as I said, you can check your textbook. There are some memorization about the periodic table, and we also learned about molecular formula and empirical formula.